Part 1 is on evaluating limits algebraically. So we're going to learn how to like factor or FOIL or multiply by a square root in order to make these limits nice limits that we can find. Okay, so first we have to start with the basics. So we have limit laws, and I just have these all written out for you. All of them should kind of make sense. So if we have the limit as x goes towards a number of f of x plus g of x, it's the same as if I split it apart into two separate limits. So the limit as x goes to a of f of x added to the limit as x goes to a of g of x. So the same works for subtraction. The same works for multiplication. Number 3 is when we have a constant. So if I had like the limit as x goes to 4 of 3 times x squared, I could pull that 3 to the front and then just worry about the limit as x goes to 4 part, right? That would be 16, and then times the 3, 48. So we can pull any numbers, like any constants, to the front of a limit. It's not affecting like the limit as x goes to a number. So same thing with division. So number 5, we can divide two limits, and we just say that it's fine as long as the limit as x goes to a of the denominator isn't equal to 0. We can't divide by 0. All right, so it says use the limit laws in the graphs of f and g below to evaluate the following limits if they exist. So this could definitely be a type of question that would be on the AP test. So they would say things like, what's the limit as x goes to -2 of f of x plus 5 g of x? So what we're doing is we're using our limit laws and we're breaking it apart into the limit as x goes to -2 of f of x added to. We can pull that 5 out, and then we do the limit as x goes to -2 of g of x. And then we find each of these things. So for the f of x graph, we look there and we're like, oh, as x gets to -2, what y value do I get closer and closer to? So what's the y value there? It looks like 3, right? So as I go from the left and the right, I'm getting closer to 3. And then the next part I have 5 times. And the limit as x goes to -2 for g of x, what's that get closer to? 2, right? Do you guys see it? Do you guys remember all this, like reading limits from graphs? All right, so we get 13 in the end, so that would be 13. So same idea on the next one. So we can do the limit as x goes to 1 of f of x, and we can multiply by the limit as x goes to 1 of g of x. So as we get closer to 1, it looks like f of x is going to 2, and g of x is going to 0. So we get 2 times 0, which is 0. Easy enough? All right, so the next one, so we can break it apart. So we have the limit as x goes to 3 of f of x divided by the limit as x goes to 3 of g of x. So for the f of x function, as we get closer to 3, it looks like 1. For the g of x, as I get closer to 3, it looks like 2. So our answer would be 1/2. Okay, so you guys try D and E. Any thoughts on D? That's right, it does not exist. And why does this whole thing not work? Because the limit as x goes to 0 for f of x, the left-hand limit and the right-hand limit went to 2 different values. So remember, that means that our limit doesn't work. It doesn't exist. So it doesn't matter that the other side, like the 3 times limit of g of x, it doesn't matter that that one, actually that one doesn't exist either, does it? Even if that one had existed, like we wouldn't do anything. We would be done as soon as we had that does not exist. Because like what's does not exist plus 7, like it still does not exist, right? So we can't like add them together or anything. All right, so the next one, so the limit as x goes to 5. So go ahead and try this one as well. So as I went towards 5 on the f of x graph, what number did I get closer and closer to? 3. And then as I went towards 5 on the g of x graph, what's the y value I get closer and closer to? Yeah, 4. Do you guys see it? Is it 4? 1, 2, 3, 4, 5. Yeah, 4. So did you guys get a total of 18? What's that? Okay, so it starts out pretty easy. You guys feel pretty good with those. It's not super challenging. All right, so then we have some more limit laws. So there's like a total of like 11 or 12 limit laws. So it's all things that make sense. So if you have like f of x, like some kind of function raised to a power. So if I had, I don't know, like the limit as x goes to 3 of x minus 4 cubed, I could just do this part first, and then I can cube it. Okay, so it seems kind of weird, but that's the part that involves the x, and then we just cube that. So the next one says the limit as x goes to a for a constant. Okay, so all of these are like functions. All of these have pictures associated with them. So if I had the line, I just told you, the line y equals c, what does the line y equals c look like? Is it vertical or horizontal? Like if I have y equals c, that would just be like this. Every single y value would have the same, like they would all be c, right? I'd have 0c, 1c, 2c, 3c. Okay, so as I go towards a certain a value, or x value, what y value do I get closer and closer to? C. That's the picture. Okay, so the limit as x goes to a of c is just c. So if you don't have an x value in there, that part is like, it doesn't matter. It just becomes the number. So how about the next one? So the limit as x goes to a of x. What do we think that one's going to be? Let's draw the picture. So if I have y equals x, and I'm getting closer to a certain a value, it goes to a, right? Because every point on the line y equals x, I would have like 1, 1, 2, 2, 3, 3, 4, 4, a, right? So it goes to a. So basically, if we're able to plug in a for an x value, we do. Okay? We're just replacing, because there was nothing that was making it undefined. There's no reason that we need a limit there. So this next one, if I have the limit as x goes to a of x to the n, it's really just becomes a to the n. There's nothing that's making it undefined. We can just plug in. So this next one is going to be the nth root of a. And then the last one, number 11, is very similar to what I did up here with the limit as x goes to 3 of x minus 4 raised to the 3. Like I can just kind of do the limit part first and then raise it to the 3. The same with a root. So if that had been like, instead of a 3, but I had some kind of root, like a 1/2 power. Oops. We know a 1/2 power is like a square root. It's the same rule. So we can put the square root around all of it, or we can do the inside part first. It doesn't matter. Does that make sense? So these are the same. All right, so it says evaluate the following limit and justify each step using limit laws. Okay, I'm going to give you the first couple steps here, and then I'm not going to do it because I think you'll see using limit laws and justifying everything is really annoying. Okay, so we're not going to do this every single time. Hopefully you'll be able to do it without. So the first thing is that we would bring the limit as x goes to -2 into both the numerator and the denominator. All right, and this is like the sum of two functions, so we could bring the limit into both pieces. So we could say, oh, well, this is the limit as x goes to -2 of x cubed minus the limit as x goes to -2 of -9. Or not -9, 9. All right, do you guys see how annoying this is? And you'd bring it into each one. So you'd say the limit as x goes to -2 of 6 minus the limit as x goes to -2 of 3x. So then these are just constants. So that's like the rule that said the limit as x goes to a of a constant is just the constant. So those just become 9 and 6. And then numbers can be pulled to the front. So I could do 3 times the limit as x goes to -2 of x, right? And then powers can go on the outside, so I can do limit as x goes to -2 of x cubed. You with me? It's really annoying writing out limit every single time, isn't it? All right, so then we get to the point where we have this and this, And that's the rule that says you're able to just plug in limit as x goes to a number of x is just equal to that number. So then you would be able to plug in -2, so you'd be like -2 minus 9 over 6 minus 3 times -2. And then you'd go from there. So -11 over 12 would be the answer. Oh, I forgot my cube. Darn, I knew I was going to do that. Is that Kyle? So let's see. So -8 minus 9 over 6 plus 6. So what, -17 over 12? Is that right? Okay, we don't want to do that every time, do we? So there have to be rules with limits even with that. So this one is going to end up being what's called the direct substitution property. So it says, no, if we had just substituted -2 into the original function, we would have gotten the answer, right? I could have just plugged in a -2 for all of these x's, and we'd be good to go. We would go directly to this step. Isn't that much easier? So the direct substitution property says, if the polynomial or rational function, if you have a polynomial or rational function and a, so the thing you're taking your x value closer and closer to, is in the domain, then you're able to just say the limit as x goes to a of that function is the same as just directly plugging in a for all of the x's. Okay, so how did we know -2 was in the function? So let's look at the original. What's the only number that isn't in the domain? X can't be what number? 2. Can it be -2 though? Yeah. -2 is two is the only number that we're not allowed to have. So our domain consists of all real numbers except for 2. So because it was in the domain for this rational function, this fraction, we're good to go. We can just plug in -2. All right, so it says, why could we not use this for the limit as x goes to 2? Well, it's not in the domain, right? So x equals 2 is not in the domain. So what would happen if I just directly plugged in 2? What would I get? Yeah, it does not exist, undefined, right? So whenever you get something that says does not exist, with limits sometimes, you might be able to manipulate them. You might be able to factor and remove the thing that made it bad. Okay, so we're going to learn those tricks. So this one says the limit as x goes to -3. So right now it looks like I can't put -3 in, right? So if I put -3 in, I get a 0 on the denominator. So it's not in the domain. But I can do a trick. I can break this limit apart and I can say, well, it's the limit as x goes to -3, and then I can factor the top. I factor into x plus 3 times x minus 3. So then the part that made it undefined, right, goes away. So we say, well, this is really the same as the limit as x goes to -3 of x minus 3. Now can I do that direct substitution? Can I plug in the -3? Sure. So when I do it, my answer is -6. So we'll be doing that a lot with limits. So we're going to try to manipulate them in some way so we can factor or remove the part that made it undefined so we can see what that limit is. And if you remember, we talked about this in a previous section. This function looks like the line y equals x minus 3. It looks like this. Just at 3, it has a hole. So there's some kind of hole on that. I don't know where it is. A hole on our function at -3, sorry. So I guess it's at -6. So over here. So at -3, we have a hole. Do you guys remember? So the value it's getting closer and closer to is -6. All right, so this one. So we have the limit as x goes to pi over 2 from the left of cotangent of x. Okay, so you kind of got to remember what your graphs look like. So let's think about this one. So this is the limit as x goes to pi over 2 from the left, and we have cosine of x divided by sine of x. Do we all agree cosine divided by sine is cotangent? Remember that. So the question is, does this make it undefined? Am I able to plug in pi over 2? What is sine of pi over 2? It's 1, right? So the bottom is 1. That's okay. We can plug in then. We're not getting undefined. Well, what's the top? What's cosine of pi over 2? 0. So 0 divided by 1 is 0. So that one was just a direct substitution. Pi over 2 was in cotangent's domain, so we were able to just plug in. Does that make sense? All right, so it says if f of x is equal to g of x everywhere except for a, so whenever x is not equal to a, then that means the limit as x goes to a of f of x has to equal the limit as x goes to a of g of x. Okay, usually I leave a little spot for a sketch for this. But basically what's happening here is if we have some kind of graph and our two functions, maybe at a there's like a hole on the graph. Draw a real big hole there. And maybe it's filled in for g of x up here. Here's my sketch. So I have some kind of function, and at a I have a hole, but another point's filled in somewhere. That's allowed, right? So we can have another point filled in somewhere. But then let's say f of x looks exactly like it, but its filled-in point is somewhere else. So it's right on top of the other curve everywhere except for that single point, which is somewhere else. Does it make sense that there are limits? So as I trace from the left and right-hand side, do the limits go to the same value? Yeah, they do. So as long as every single x value has the same y value, except at maybe that one point, their limits will be the same. All right, so here's some examples. So it says use algebraic methods such as FOIL, factoring, multiplying by the conjugate, and finding common denominators in order to solve these. So this first one is just a piecewise function. So let's think about what this piecewise function looks like. So we have the limit as x goes to 1, and it says our function looks like the line y equals x minus 2 if x is not equal to 1. So do you guys all know how to graph y equals x minus 2? So up 1, right 1, up 1, right 1. Except at 1, there's a hole there. Get a little close to my tick marks. And then it says, well, at 1, we have the point 1, 5. Okay, so it's the line, except there's a hole right here, and that hole has a filled-in point above it somewhere at 1, 5. Okay, what would the limit then as x goes to 1 be? What was it? Negative 1, yeah. Because we just used the line. We don't worry about that single point that was elsewhere. If you remember the definition of a limit, it's the y value that we get closer and closer to as the x value gets closer to a certain number from both the right and left, right? So as we trace our fingers from the right and the left, closer to an x value of 1 along the curve, we're getting closer to negative 1. So that answer is negative 1. All right, so this next one, so what's wrong with it? So in number 2, right now, can I put in h equals 0? No, because it's not in the domain, right? It doesn't work. So maybe we can manipulate it in some way to simplify this out so that we can. So that's where we're using FOIL. So if you remember how to FOIL, we're going to take that 2 minus h and we're going to multiply by 2 minus h. Now every time we're doing limit problems, we have to write limit until we're able to plug in. Everybody always hates that. One year I told my class that they could just do L squiggle and I'd know what it meant, which was fine until people were like, oh, I just did that on the AP test. I was like, dang it. Like, I meant for like homework, you could write L squiggle. So you can't write L squiggle anymore, thanks to Dimitri Georgakopoulos, who like would not let you do that. He did L squiggle on his test. All right, so here we go. So we're going to FOIL it out. So we get the limit, so we still have to write limit. So we get 4 minus 4h plus h squared minus 4 all over h. Do we see some magic happening here? 4 minus 4 goes away. The h goes into everything in the numerator, so I can pull out an h, and I'd have negative 4 plus h all over h. So then those h's go away. So now I have the limit as h goes to 0 of negative 4 plus h. Can I plug in h and it's okay? Yep, so my answer is negative 4. So you could do like your table method and get closer to negative 4 from the right and left. You could graph it. You could see what it gets closer and closer to. It will get closer to negative 4. All right, so the next one, number 3, says factoring. So we're going to factor the numerator and denominator. So right now, the 4 is what's making it bad because we have x minus 4 on the bottom. I'm going to guess that when we factor, we probably have x minus 4 on the top. Probably, right? That's probably why it's going to work out in the end. But not always. So if I have x minus 4, I'm going to need the other one to be x minus 2 so that the last numbers multiplied to be 8. And our outer and inner swoops combined to be that negative 6x. So the x minus 4's go away. Are we able to plug in 4 now? Yeah, so we get 4 minus 2, which is 2. That's our answer. Okay, so the next one's still factoring. Do you guys remember how to factor x cubed minus 8? Yeah, there's a pattern to it. I always call it the SOAP formula. Do you guys know why it's SOAP? Same, opposite, always positive. Have you guys heard any of this? No, you have no idea what I'm talking about. Okay, so let me give you an example. So if I have 8x cubed minus 125. So if you ever need like extra space and I do something like this where I give you another example, there's always additional notes in the back of your notes. So you should have blank pages back there, hopefully. All right, so this is what we would call the difference of two cubes, right? So do you recognize what's being cubed? So in order to get 8x cubed, it's 2x times 2x times 2x. In order to get 125, it's 5 times 5 times 5. Okay, so the first thing that I always do is I think about what's being cubed and I write it. So I'm like, oh, this is cubed and this is cubed. From there, do you guys know how it breaks up? It breaks into a binomial and a trinomial. Weird math words. Binomial 2 terms, trinomial 3 terms. So we're going to have a tiny parenthesis and a longer parenthesis there. Okay, we then drop the cubes to get this first parenthesis. So in the first parenthesis, we're just going to have 2x minus 5. So that's why I kind of identify what's being cubed. Okay, let's think about this. How am I possibly going to get the 8x cubed? What do I need in this first spot? So that these two will multiply to be 8x cubed. Yeah, I need 4x squared. So basically I'm squaring the item that was right here. So the 2x. I'm squaring this. I'm also going to square the 5. And I'm going to put it at the end. So what do I get when I do 5 squared? 5 squared. Come on, guys. Not 125, 25. And if you notice that if I FOIL things out right now, I'd at least have my 8x cubed and I'd at least have my negative 125. But your outer and inner terms are going to have to all cancel each other out somehow. So we need one more thing in the middle. So what we do is we take those two blue circles that I have and we multiply them together. So what do you get when you do 2x times 5? 10x. So our signs in the end are the same as what they were originally. So see how we had a minus originally? So we have a minus. Opposite what it was originally. And then the last one is always positive. So we do plus and then plus there. And you could multiply that all out. Right, distribute the 2x, distribute the negative 3, combine all your like terms, and you would get 8x cubed minus 125. Do you guys want to try another one? Or do you guys feel okay with that? So what if I had the sum? So what if I had x cubed plus 8y cubed? So you'd first identify what's being cubed. So you have x and you have 2y. You'd then break it into the binomial and the trinomial. You drop the cubes, 8x plus 2y. So just drop the cubes and wrote each of these things. In the first spot, I square the first item, so x squared. In the last spot, I square the last item. So I'm going to have x squared, and when I square my 2y, I get 4y squared. So right now, I'm getting the x cubed and the 8y cubed. Okay, but I have to get rid of the outer and inner stuff. So I multiply those two things together, 2xy, same, opposite, always positive. So plus minus plus. Okay. So that brings us to number 4. So we're identifying what's being cubed. It's x is being cubed, minus 2 is being cubed. So we drop the cubes and write x minus 2. We do x squared and we do 4 on the end. What do we write in the middle? 2x. And then we go and we put in our signs. So same, opposite, always positive. We divide by x minus 2. So what happens here? X minus 2's go away. And we can now plug in 2. So when we plug in 2, we get 4 plus 4 plus 4, which is 12. So our answer is 12. Does that make sense? Okay, so let's say you're on the AP test and you totally forget. Like, there's always other ways to do things. I think that's the big thing. Like, for people to be successful math students, you're not just memorizing every single method. You're, like, thinking about, well, what's another way I can do this problem if you forget something? So if you forgot how to do the soap thing, which many of you guys did from Algebra 2, I'm going to guess all of you probably forgot how to do that. Except maybe if it's still fresh in your mind, like you had Algebra 2 last year or something. All right, so most of you guys probably forgot that. So what I would do is I would remember synthetic division. Do you guys remember synthetic division? You looked up like, wait, what? So if you have like x cubed minus 8 divided by x minus 2, you could put 2 in the backwards L, 1x cubed, 0x squared, 0x minus 8, and you can divide it out. So we drop the 1. 2 times 1 is 2, add straight down we get 2. 2 times 2 is 4, add straight down we get 4. 2 times 4 is 8, add straight down we get 0. And what this represents is x squared plus 2x plus 4, which is exactly what that other factor was. It was right here, x squared plus 2x plus 4. And then the 2 represents the factor x minus 2, right? So you could factor it that way as well. Did I lose you guys? Are you like, we're not doing synthetic division? You could do that if you want to. All right, so let's try the next one. So the next one has a square root in it. So let's check to see if we can do the direct substitution. So tell me, can you? Can you plug in t equals 0? No. So we got something weird going on. So when you see a square root, a lot of times you're able to rationalize. You're able to multiply by its conjugate. Do you guys know what these words mean, multiply by conjugate? So if I had like 3 minus root 2, let's say I had that on the bottom of a fraction. So in Algebra 2, do you guys remember what we multiplied by to get rid of the square root of 2 on the bottom? Not just root 2, because we had 3 minus root 2. 3 plus root 2, that's called the conjugate. And we did it on the top and bottom so that the square root went on the top, but then the bottom, all of that FOILed out and the square root went away. Okay, that's what we're doing with this problem, only now it's in the numerator. So we have a square root in the numerator, which is fine. So we're going to do the same idea where we're going to rationalize. So we're going to multiply by the square root of t squared plus 9, and then instead of minus 3, we're going to do plus 3. And we do that on the top and the bottom. Okay, so it doesn't look like anything exciting right now. So we have the limit as t goes to 0, and we FOIL this top out. And the bottom, I'm going to leave the t squared out. So I'm going to leave it like not multiplied out. So I'm just going to leave it like that because I'm probably going to have a t squared go away. T squared is what's making it bad. It's what makes it undefined, right? So I'm hoping that something's going to cancel that out. Okay, so think about FOILing the top. So what do we get when we multiply the first term? So the two things that are under that square root. Yeah, it's just t squared plus 9, right? Because it was the square root of t squared plus 9 times another square root of t squared plus 9, so the square roots go away. The outer and inner, what happens there? The outer term was this times this, the inner term was this times this. One of them's 3 times the square root, and one of them's minus 3 times the square root, so they go away, right? That's why we multiplied by the conjugate. So outer and inner are gone. What about last? Minus 9, right? Do we like that? Cancel, cancel. So yeah, we get t squared. So sometimes I do all this canceling on one, but for the sake of your notes, I'll write it out. So what's happening now? T squared. What's left on the top? A 1. So we get 1 over, and are we able to plug in 0 now? Yeah, we have the square root of 9 plus 3, which is 1 over 3 plus 3. So 1/6 is our answer. So once you're able to plug in, you don't have to write limit anymore. Does that make sense? All right, so let's do the same thing on this one. So we're going to multiply by the conjugate. So the first step you're going to do is you're going to multiply by the square root of x plus 7 plus 4 on the top and bottom. And my advice is to leave the x minus 9 factored to the front, or factored. So it's going to be like x minus 9 on the bottom, and then the square root of x plus 7 plus 4. Oops. I love when I do that. So figure out what the numerator is. Claire, do you have your notes? So when you FOIL out the top, you should get x plus 7 when you multiply the square root parts. What about the last number? Minus 16, right? 4 times 4. So be careful. Sometimes on problems, like maybe I had like square root of 3 and square root of 3 on the last one. Sometimes I'll have like square roots there as well. And people mess that up. So if I had square root of 3 times square root of 3, it would have been 3. Same here. If I had like square root of 4 times square root of 4, it would be 4. But these are just plain 4s. So you should get 16. So what does the whole numerator become? X minus 9. Do you see why I left that x minus 9 factored out? Yeah, when people go a step too far and multiply it out, it gets really confusing. So the x minus 9's cancel. Now we're able to plug in 9. So we have 1 on top. We have the square root of 16 plus 4. So we get 1/8 out. Okay, makes sense? All right, so the next trick is common denominators. So this is what we would call a complex fraction. You guys did complex fractions way back when in Algebra 2. So complex fractions can be simplified. We can combine all of these. We don't typically leave like, things like, oh, my answer is 1 over 5/6. We would never do that, right? We never leave a fraction within a fraction. So when you see a complex fraction, just start simplifying. Start combining like terms, right? So on the bottom, I want to combine these fractions by getting common denominators. So I'm going to multiply that first one. I still have x on top. I'm going to multiply the first one by 4 over 4, sorry. So 4 over 4. And I'm going to multiply that second one, that negative 1/4, by what? So I get common denominators. X plus 4 over x plus 4. Did you guys see that? So I continue combining. So I'm like, okay, I have the limit as x goes to negative 4. And I do x over. And here's the tricky part. I'm definitely getting common denominators, so I'm going to have 4 times x plus 4 on the bottom. Okay, so everybody write what you think that numerator, the numerator on the denominator, what do you guys think this is? Write it down on your paper. So a lot of people will write 4 minus x plus 4 like this. Did you guys write that? You actually need parentheses around that because you're subtracting out this entire term. So see how you have a minus there? So you have to subtract out the entire x minus 4. So make sure you put parentheses around the x minus 4. So we get the limit as x goes to negative 4, and we have x. Let me write it as x divided by. You guys remember, like, I call this the old school division sign. You guys remember doing that division sign in elementary school, which just disappeared. We never used it again, right? Once you get to high school, you rarely see that. So I'm going to use that division sign. And I'm dividing by that fraction. So I have 4 minus x minus 4. So I get negative x. Do you guys see how that simplifies down to negative x? So I'm dividing by negative x over 4 times x plus 4. Now do you guys see what we need to do? So we have this old school division sign. One of my students looked it up because I guess it bothered him that I called it the old school division sign. It's called an obelus. Who knew? All right, so we have the limit as x goes to negative 4. And we're going to do x times, and since we had divide by a fraction, we're going to flip that fraction. So we're going to have 4 times x plus 4, and then a negative x on the bottom. Make sense? So what cancels? This cancels with this, and we're left with a negative 1. And then we can plug in the negative 4. So we have 4 times negative 4 plus 4 divided by negative 1. So what does this whole thing become? 0.